So in the previous lecture, we started our discussion on the stream function, vorticity stream function formulation of 2D fluid flow equations. So we derived the equations for vorticity and stream function, which are these equations, omega psi equations. And then we started with the process of finite volume discretization of these, of the stream function equation to start with. Okay. So let's quickly recap the process of this finite volume discretization, and then we'll continue from here. So what we do is we define a control volume or control volumes from the mesh that we have. So the red control volume is what we have defined for the I comma jth nodal point, and then we integrate the equation that we have to solve over this control volume. So we are satisfying the equation in an integrated sense, and that is kind of good for some fields because there are some fields that we want to conserve, for example mass. So if you say that this mass equation, for example, not this one but a mass equation for example, is satisfied in an integrated sense over a volume, and then you do it for all the volumes, then overall the mass will be conserved. Whereas if you discretize it using a finite difference approach, where the concept of integral over a volume is not satisfied by definition, right? So then we use the Gauss divergence theorem to convert the volume integral in the first term into a surface integral. So that results in a summation over 4 terms because our volume has 4 faces. Again, in 2D it has 4 edges, but we'll still call it faces to keep the terminology general. So then we have, as you can see in the beginning of this next page, you get a summation over 4 faces, east, west, north and south, and then we simply have to expand it depending on which face we are dealing with. So we get 4 terms in the equation, and that's where we stopped. Now from here we'll have to proceed further to get a discretized equation. So then that depends on how we define these derivatives on the boundaries. So for example, del psi by del x on the east face has to be defined in terms of quantities which are to be calculated. For example, the I comma jth psi value, or I plus 1, I minus 1, j plus 1, j minus 1, and so on. Because ultimately you have to write these in terms of the unknowns. Is that clear? Any questions till this point? Okay. It's much easier if I start from here in the same lecture. Right. So next we have to convert these derivatives on the boundaries in terms of quantities which are the unknowns in this problem. So let's go with the first term, which is del psi by del x on the east face. Let's look at the east face, which is this one on the right. To evaluate del psi by del x on the east face, the easiest thing I can do is I can do some sort of a center difference, right? One forward point, one backward point. Now you'll see that this is in finite volumes we have to find out ways to define derivatives or gradients at the boundaries. That's very important. So on the east face we can write del psi by del x as the so del psi by del x on the east face can be written as psi on the capital E cell minus psi at the P cell divided by whatever the size of the cell is, that is delta x, right? I'm assuming that we are in the middle of this cell, but if we are not in the middle, the way we have defined control volume is slightly different for non-homogeneous meshes. In that case, you have to figure out a way depending on what is the position of the east face. So some sort of ideas can be used, but here, to keep things simple, we have defined completely homogeneous mesh. Is that clear? So this becomes psi capital E minus psi p upon delta x times delta y. Then for the west face, if you have to define derivative, now again I introduce the same idea, psi capital P minus psi w upon delta x. So psi capital E is nothing but psi I plus 1 comma j, and psi p is I comma j. Similarly, psi capital W is psi I minus 1 comma j, and then psi north becomes psi I comma j plus 1. Alright. Now, if you simplify the terms, interestingly, what you'll see is that the expression is going to be exactly the same as what we had for the center difference method, infinite difference, which is not always the case. It's just that for this case we got it. So this will simplify to psi I minus 1 comma j minus 2 psi I comma j plus psi I plus 1 comma j. Now the reason I am writing this in this form is just to show you that this is what we get. So what we have done is we also multiplied this by delta x times, divided by delta x times delta y, which is the volume of the cell. So when you divide it, so let's write it at delta x times delta y times this whole quantity. For now, I mean the way we have written things. Okay. Now this was just one term. The other term was our this one, omega times d capital omega integrated over the volume. So this we had written as omega p times delta x delta y. So the overall equation is the sum of these two. So I can now write it as, now I'll divide everything by delta x delta y. So I get this whole expression that I've just written, plus omega I comma j is equal to 0. Or I can actually write it as this is equal to minus omega I comma j. Is that clear? just note that it's not always the case that we get the same form. We may get different form. That's the beauty. We may get a different form, but as long as the form is consistent, as our delta x and delta y tend to 0, the solution of this discretized equation will tend to the exact solution. So that's the whole idea, that there's no unique approximation. There are many different approximations possible. So every method may give you a different approximation in terms of the discrete equation. So that was the stream function equation. Now we'll move on to the vorticity equation. So this was the omega equation. We had a transient term, we had a convective term written in the conservative form, and then on the right hand side we have a diffusive term. Right. So what we'll do is we'll move terms to the left hand side and make this equal to 0, and then we'll integrate this over our red control volume, the center of which is the point capital P, which is I comma j, and then we have east point. So these capital letters are denoting the nodal points, and this is your control volume capital omega, and then the surface is given as gamma. So we integrate this over the whole control volume. So this is what we do, and we'll say that we'll satisfy this equation in this form, and we'll proceed from here using the finite volume method. So we have three terms here, so let's write them as 1, 2 and 3. So we'll deal with each one of them separately and then combine them together. So let's look at the first term, which is integral of del omega by del t over the volume. So this again, just like this is simply written as omega at n plus 1th time minus omega at the nth time. They're both for the central point. Okay. And the way we did last time, that we'll say that we will assume this omega p values to be average over the whole control volume. So the same way we wrote the integral of omega times d capital omega as omega p times delta x delta y, we'll write this as the derivative of this times delta x delta y. Delta x delta y is the volume of the control volume. So again, one thing to remember in finite volume method is that whatever values we are talking about, they are the average values over the, so the way finite volume considers the different terms is that it considers omega I comma j, for example, or omega capital P as the average value over the control volume. Whereas in finite difference method, you're talking about the actual value at that point. So there is a difference. I mean, if I give you the exact value and I told you what is finite volume representing and what is finite difference representing, finite difference will just take the value at that point. Whereas finite volume will average it over the control volume and then give you that. So that is what we are calculating here. So it's important to understand what we will end up with. So we will not end up with the exact value, we will end up with the average value over the control volume. So larger volume you take, the larger average it will calculate. That's how it is defined. Finite volume method. Okay, so that's the first term. Let's move on to the second term. Now this time we can use the Gauss divergence theorem to simplify this. So we'll convert this to an area integral over capital gamma, and this becomes u omega dot n hat times d gamma, where n hat is the outward normal from the surface, where d gamma is for the surface that is under consideration for the integral, and this is a closed integral. So we put a circle over the integral because it's a closed surface, because every volume is enclosed by a closed surface. Right. So similarly, like we did in the previous lecture. So u omega dot n hat for the east face. I mean the small e. We have small e, small w, small n, and small s. So for the eastern face, I can write this as. Remember, n hat becomes I hat here. And well, I've been writing sometimes u hat, sometimes v hat, sorry, a v vector or u vector, but they mean the same thing. Sometimes I denote u vector as u comma v, sometimes I might be writing v vector as u comma v. They are used interchangeably here. So whenever you have a vector over u or v, that denotes the velocity vector terms u comma components u comma v. Right. So when you take the east face, the velocity vector dot I hat becomes the u component. That becomes u times omega. Now this is calculated over the east face times the area of the eastern face, which is simply delta y. Now for the west face, you get u times omega with a negative sign, because we have the outward normal is in the minus I hat direction times delta y. For the north face, we'll get a v times omega on the north face times delta x, and for the south face, we'll get a negative v times omega over the south face times delta x. So this is how we expand it for the four faces. It's a very standard finite volume technique that I'm using here. Now the question is how, so it's a product of u times omega on different faces, or v times omega, whichever face we're talking about. So let's take the eastern face. So we have u times omega. How do I write u and omega on the eastern faces? Now just like last time you want to write it as a center difference, or is this time there's no derivative, so we'll use some sort of an average of the two values. To define the u value at the eastern face, I can use u at the capital E cell plus u at the P divided by 2. So take the value, you take an average of the two values. And what about omega? No, omega is what we are calculating. Omega is not known. In fact, u is known for this equation. Omega is what we are calculating, but we'll not worry about that. We'll just so omega can be calculated using a center average, like the way I've done here, but that could be a problem. Remember upwinding? This is a convective term. So now we are bringing all those ideas together. So to define the omega on the eastern face, just a minute. Yeah.
When we wrote the stream function equation, then you said that omega is equal.
For the stream function equation, yes. These are two different equations. So when you are solving the stream function equation, that is done after the omega equation. So I'll write the algorithm today, so this will be much clearer. So this is an equation for omega. So you are using this equation to solve for the vorticity omega in this equation. So omega is the unknown here. Right. So omega on the eastern face, if you use a center average, it becomes a problem. This is unstable, somewhat unstable. I mean, not completely, because you have a diffusion term also. This is not a purely hyperbolic equation like a 1D wave equation. In 1D wave equation, it's purely unstable, this center average, center difference. But for equations which also have a diffusive term on the right hand side, it may not be completely unstable, but it could be. Okay, so the best thing to do is to use upwinding. So in upwinding, what we do is we use an upwind value. So to define omega on the eastern face, we will use omega p if our flux of mass is greater than 0, or we'll use omega e the flux is less than 0. So if flux of mass, basically if the flow is happening from left to right, then we'll say that the flux is positive. Flux is u times omega. So if you can also call it if so if flux is greater than 0, then we'll say that our material is going from left to right. So then we will define omega small e as omega capital P, because the information is coming from left to right. And if the flux is negative, then we'll say that the information is going from right to left. So we'll call it omega capital E. So this is upwinding. Okay, so we must remember there's always sometimes a confusion that why are we doing center average for u and then upwinding for omega? So omega is what we are solving for. So this is the unknown, and u is just a coefficient. Because in this equation, u is a coefficient for this. U is sort of assumed to be known here. You put the value of u. But omega is what you're calculating. So omega is the unknown here. So omega is what you have to upwind, not u. So what we have written here for upwinding is actually called a simple upwind. So let's talk a bit more about upwinding. So let's say we have this control volume, and I'll also draw a couple of other control volumes. So let's say this is my control volume P, and we have cells here, and let's say the flux is positive, so flux is greater than 0. So and this phase that we have, this phase we'll call F. Okay, so let's say we are trying to calculate the value of the unknown, let's say omega over the phase F. So we just discussed if the flux is greater than 0, then it's like this. So a simple upwind would be written as omega on the phase small f is, we'll call it capital U, and this one we'll call capital W. This is a notation. You ultimately you have to write things in terms of I and j, I comma j indices. So omega on the phase f in a simple upwind is written as omega capital U. The information is coming from left to right, so we write it as omega capital U. But we can also, so this is first order upwind. We saw that in finite difference that if we use this kind of an approach, the truncation error is of the order of delta x or delta y, depending on which direction you're talking about. So we can also have second order upwind. Well, we'll not derive it here, but this can be written as the coefficient 3 by 2 times omega capital U minus omega capital W by 2. So this second order upwind, as we discussed earlier, will consider two upwind points, omega capital U and omega capital W. So this results in a scheme which is second order. So this is how you go for higher order schemes in finite volumes, that when you are finally converting that surface integral expressions into discrete unknowns, then you have to, depending on which scheme you are using, you have to replace, for in this case, an expression for omega on the face. In some cases, you have derivatives on the face written as in terms of higher order schemes. And there are higher, there's a quadratic scheme as well, but I'll not go into details of all these. Okay. And then if you had the flux to be negative, let's say the flux was negative. So we'll call, just because things are like this, so we'll call this upwind and this becomes W. Now this whole thing also works for this now, the way we have defined, because simple upwind is omega small f is omega capital U. So this lets us define the same loop, as long as you have defined what capital U and capital W mean. When you, I'll share a code with you over the next week, and you can have a look at it. Any questions? Now with higher order schemes, what can happen is that, I mean, it's always good to use higher order schemes in the sense that they give you a more accurate result. But you'll see that now this stencil, if I were to write the stencil here, it becomes more complicated, because now I am including 2 upwind points or maybe 3 upwind points and so on. So what will happen is that in each equation that you write for each I comma j, you'll have more number of terms. So your matrix sort of has more terms in it. Okay, so there's more communication, more calculations that are happening, so it becomes more complicated to deal with. On the other hand, the convergence also becomes difficult. So it's seen that with simple schemes or lower order schemes, they tend to give you a result. Numerically, they are much more convergent in the sense that they will not diverge. So simple schemes are always more numerically tractable to handle. Whereas it's not always the case, but in general, we have seen that the more terms you include, the more complications that can appear. So what we do is, practically we always start with, so if you have, because you have multiple terms, you just don't have convective term now. You also have a transient term, you also have a diffusion term that we'll talk about now. So since you have all the terms in the equation, you always tend to start with simple. So you choose simple upwind, you choose some sort of center difference, not higher order differencing, and so on. In transient term also use the order delta t term or delta t expression. So this way, what will happen is that we will get some result to start with, and then we'll increase the accuracy. We'll increase the discretization order for one particular term, and then see what happens and so on. If you start all of them with higher order terms, the most probable thing is that it will just crash. It will not converge. That comes with experience, but this is just a note for you that higher order schemes, I'll just write it here. So difficult convergence. And the stencil is dense. So this was the convective term, that was term number 2. And you do it for each term. So we just did it for the east phase, for the west north and south also you have to write expressions. Next comes the diffusion term, term number 3. Now, term number 3 is what we dealt with in the stream function equation. In stream function, we had the Laplacian of psi. Here we have the Laplacian of omega. So we'll have the same expression. Okay. So I'll not show all the steps because we already have done that in the previous case. So this will simply become that omega times the same as the center difference approach, where you have delta x square in the denominator and delta x delta y. So I'll not repeat that.
The multiplication of delta x delta y.
Right, sorry, yes, delta x and delta. Thank you. Yeah. So once we have written all the terms together, then we divide everything by delta x delta y, because it will come out as that's okay. Can or cannot do it, doesn't really matter. This is how we write the equations. So I'm not doing everything here, but when you will see the code, then make sure that you fill in the gaps. So between this and the code, you will have to write all the complete expression and then you can see the code. But we'll write the code in such a way so that it's very similar to the way we have done. So we write term number 1, term number 2, term number 3. So you can map it to what we have discussed in the lecture. So let me discuss the lab problem, but it won't be a lab. I'll just give you a solution this time because next week is off. But I'll want to discuss the problem that you'll be seeing the solution for, and then a very similar problem will be given as an assignment number 2. So you will have literally like to copy snippets of code from here for assignment number 2, but the boundary will be different. So you'll have to change the loop orders and so on. But there'll be difference, but the equations will be handled in the same way. So we'll call it lab problem. Usually we have it as a lab. So this is called, in fact I showed you a demo of this in the beginning of the course. It's called a backward facing step. So we have this kind of a tube with a sudden change in area, and the flow is happening from here. So this is called inlet, and the flow leaves from here. So that's called outlet. It's a 2D problem. And then we have a parabolic flow profile. So it's a laminar situation. So and the size of the inlet is capital L. This is L2. The step size is LC, and this is called L3. These are just dimensions of your step, backward facing step. And what you see is that when the flow enters and there is sudden expansion, the flow takes this kind of streamlines. So the flow inside this region only recirculates. It does not mix with the other flow. Now that's very important. If you think like a mechanical engineer, you will want to know these regions of recirculation, because the effective diameter of the pipe is not the same as what we see here. Distance over which, and the other thing is if some material in the fluid keeps recirculating, it starts depositing on the edges as well. Many things associated with this, but this is not the aim of this course, so we'll not go beyond that. It's important to understand the size of this recirculation zone. So we will give that as LR. This is LR that we have to find from the solution. Right. So this is the problem, and you'll have to use some values of L, L2, LC, and L3 will be given that you have to work with, and we'll have to find the steady state velocity profile, and then find the recirculation zone length LR from there, and we have to compare that against some benchmark. So there have been, in fact, experiments done. So you can validate it against experiments. Some very good experiments have been done many years ago, published works. So we can use that. But in this case, I'll give you the value that you're supposed to get, and then you can run the code. The code will be given to you. So you just run it and play around with it and understand how it's working. Now, since it's a 2D problem, we'll use the vorticity stream function approach. So you solve the vorticity and stream function equation, and from there we extract the velocity values, and from there we can extract the recirculation zone length. Okay. I won't discuss any more about the problem or the algorithm here. What I'll do is in the Jupyter notebook, I'll include all the details so that you can read it there. There are more interesting things that I want to talk about here. How to deal with the boundary condition. We still haven't talked about boundary condition. We talked about the internal equation. But these are not standard fields. Omega, I mean, what is omega on the boundary? What is stream function on the boundary? These things are what we have to now talk about to be able to deal with the boundaries. So let's start with whatever I can discuss, I'll discuss. Others will be shared to you for you to read. But that's very much a part of the syllabus. Okay, so let's start with the vorticity omega on a wall. Let's take, for instance, let's take a wall which is a top wall. You'll have walls on the left, bottom, left, right, whatever. So let's take a top wall. So for velocity, we know the boundary conditions. So if it's a non-permeable wall, V is equal to 0. And if we take the no-slip condition, which is quite true, then the U is 0. So if you take a non-permeable no-slip wall, then on the boundary, we'll have U equal to V equal to 0. Okay. So this boundary point will be called small b, and this point will be called interior. So rather than using I and j, I'm using this b and int here because this sort of makes it a bit more general. So omega is defined as del v by del x minus del u by del y, and that is we have to find omega on the boundary. But that is unknown. I mean, we do not know the gradients of velocities for now because we haven't solving for that. So the other way to do is we will use the stream function, because stream function is readily calculated in the previous step. It's better to use the stream function here. So let's write with omega. Let's write omega as minus Laplacian of psi. So omega on the boundary becomes minus the Laplacian of psi on the boundary, which is basically minus del 2 psi by del x2 plus del 2 psi by del y2 evaluated on the boundary. Now the boundary is also a streamline, right? So this is a known fact, because streamline is where the velocity components are zero. The velocity is tangential, and no flow can pass through a streamline. So from that, boundary also becomes a streamline because there's no flow crossing the streamline. Okay. So since this top boundary is also a streamline, so that means del psi by del x is 0 because psi is constant over the top boundary. Okay. So we'll so if del psi by del x is 0 all over the boundary, then the derivative of del psi by del x will also be 0 all over the boundary. So this is 0 because psi is equal to constant on top, or on just the boundary I'll write here because b means the top boundary here. Well, I'm using b for the point b as well. So let's call it psi equal to constant on top boundary. Okay, so I can write my omega b on the point B as simply minus del 2 psi by del y 2 evaluated on the boundary. So I have to figure out a way to write the expression for del 2 psi by del y 2. So we to write now I'm changing gears here. So to write psi at the interior point, I can write it in terms of psi at B using Taylor series. Okay. Now what is this term del psi by del y? That is u. And what is u on the boundary?
0.
0. So this is 0 because u is 0 on boundary. So I'll just take the first term in these. So what we get is from here we can use this to calculate del 2 psi by del y2. So del 2 psi by del y2 on the boundary simply becomes twice of psi interior minus psi on the boundary divided by delta y squared. Plus you will have order delta y terms which we are neglecting here. So omega on the boundary so therefore becomes minus of 2 upon delta y squared times psi int minus psi b. Okay, so on the walls we give this as a Dirichlet boundary condition for omega. Clear?
Do we know real terms?
Because we are solving the omega equation here, because omega boundary is needed for omega equation. So the way we solve them, we know that the psi equation already is solved. Because when we are using, in fact, you're right. The way we solve it now, we solve psi first and then we solve omega. No, sorry, we solve omega first, then we solve psi. So in this case, we'll have to use the values of psi from previous time step. So that is a bit erroneous. But the good thing here is that since for the problem that we are dealing with, we are solving a steady state solution. So the transients will not matter. We'll be using a false transient approach here. So what that means is, although we are using a transient approach, but what we are interested in is the final solution at when the solution stops changing with time. So for that reason, if we tend to use psi from the previous time step in this boundary condition, the way we deal with it, ultimately it converts to the right solution. The transients may not be very accurate. So that's the thing. Now I'll not be able to discuss each and every situation with you, because then it becomes too complicated. This is just a first level CFD course. So we'll, in this case, if you're dealing with steady state, then this approach will work. But there are many alternate approaches, but this is just one of them that we are discussing in the class. And this will get you started. Okay, so it's time now, so I'll stop the lecture here. Now there are a few things to discuss before you can actually start solving the problem. So that what I'll do is I'll record a supplementary part of this lecture, which will be 15 to 20 more minutes as to how to deal with boundary conditions. And if possible, I'll also include the algorithm of the code that you have to not write but understand. Okay.